Here we go. We are live. Woohoo! All right. Today's Frontside Lunch and Learn is on Make-a-Lisp. I guess I should start out why I think this is a good idea. So, if you've never heard of Make-a-Lisp, or sorry, if you've never heard of Lisp, it's a programming language. Maybe it's like a little bit esoteric, but of all the programming languages, I feel as though Lisp kind of lays the most thinly on top of the core of what computation is all about, of evaluating, taking a value or a set of values and evaluating new values. Like there's no artifice, there's no ceremony, there's no anything on top of it. You know, if computation is this sculpture, I feel like sometimes we, with our JavaScript and our C and our Java and even our Haskell and stuff, we cover it with foam padding. But with Lisp, I feel like you're taking a rough sketch. You know, you're just laying this paper type thing on there, and so I think it gets you close to these core fundamental principles, but it's also something that you can really like grasp onto very easily. And so, you know, I was always very intrigued by the concept of Lisp. I had a lot of fun using Clojure, which is just a great language. And the thought had never crossed that I might make my own. But there's someone out there on the internet who actually said, hey, making a Lisp is really fun, and you get to have the same set of insights as you build it that, you know, the original implementers of Lisp must have had. And so it's called Make-a-Lisp, and it's its own dialect of Lisp called Mal, for Make-a-Lisp. But it has its own rules, it has its own, you know, unique semantics. But what's cool about it is you don't get an implementation, you get a set of milestones and roadmaps and a test suite at each point to know that you've got it right. And so what they've done is basically set up guardrails all the way up Lisp Mountain. And so you're able to climb it and know, am I going in the right way or not? So, with that said, let me get started. For some reason, okay, this is screen here. And so here's the, let's see. Whoa. Okay, let's start. So here's the GitHub repo, and I'll make sure to include a link to that. And you can see it not only has a guide to how to build your Lisp, but it's actually got, these are all of the implementation languages with which people have built. So there's something like, I think there's about over 60 different languages. And there's some that are, you know, really mainstream and some that are pretty obscure. So someone actually implemented Lisp in PostScript. Someone implemented it in Rust, someone implemented it, there's a couple that caught my mind. Yeah, someone actually, I think it was the original maker of this repository did it with Makefiles. They implemented a Lisp repository with Makefiles, but the beauty of this is you can really, yeah. But I think one of the coolest things, and then of course one of the milestones is that, like, I think there are about 8 or 9 steps, and one of the milestones is you implement a Mal interpreter in Mal. So you make it self-hosting. So, but you develop functions, Lambda syntax, macro system, all, and I'm currently on step 3, but I found it all very digestible so far. Step 3 out of 7. What's that? How many steps are there? I think 7 or 8. And so I'll just go over kind of the first set of steps. So you clone the repository, and there's a bunch of nasty setup, but let me go ahead and I'm going to go ahead and check out where I was here. So this is okay. So the test harness that you get is just a simple make file that lets you run either a REPL, which stands for read, evaluate, print loop, or actually run the test suite. So the implementation that I'm calling mine is Node. There actually already is an ES6 implementation, but I'm doing it in JavaScript first, and then I'm going to do it. I'm going to do it in. I was originally looking to do it in WebAssembly, but then I was like, let me just kill one bird with one stone instead of two birds with one stone. And so you say, I want to run the test suite for step 0 of using Node. So I want to say make test caret Node, the implementation, and step 0. And so that'll actually run my test suite. It'll make sure that I did the passing tests. So step 0 is just making sure that you have a simple read, evaluate, print loop. And so if we look at the step 0 in Node, this is what it looks like. We read a string, we evaluate that string, which is just going to return that string, and then we print the value that's returned. And so what's nice is he starts you out with just setting up the REPL and setting up the interpreter so that you can plug so that his test harness can evaluate what you're feeding to it. So they return nothing, and you can see here's my loop print eval read string. But that basic structure is going to be kept into effect the entire time. And so this right here, these 30 lines is the core of any Lisp interpreter. And minus really this stuff which is related to the terminal. So this is Node. This is very Node specific. But I ran the test suite, and I can see this running if I say make, instead of test, I say make REPL. It boots up my REPL. And right now, this REPL, all it does is it prints exactly what you give it. So I can say this is a REPL, and it points that. This stuff doesn't have to be balanced. I can put whatever symbols into it I want. All I'm doing is it's reading, it's evaluating, and it's printing. Just so happens that this evaluation is a no-op. So that's pretty nice. Then step 1 is to actually to implement the reader. So to implement the Lisp syntax. So here there's no interpretation. If I say foo, it's just the string foo. So step 1 is to implement the syntax. And oh, I should point this out. There's the key to this is there's an actual guide here. There's nine steps. And so it's actually a pretty cool meta guide. And gives you kind of that's the outline of what we just saw. Was I want to take a string, I want to eval it, but this current eval just passes it through, and then I print, which is also a pass through. But everything, and then we just gradually fill in the different parts. But this is the basic skeleton of the Lisp interpreter itself. So the next step right here is to actually read something into an abstract syntax tree. And this was definitely a magical moment for me, because parsing JavaScript syntax or parsing Java syntax or parsing Ruby syntax is just an exercise in, man, how would you ever even do that? But it turns out that if you use S expressions, it's pretty easy. So if I go to my implementation of step 2, real quick. Oh wait, no, I want to do hold on. What? Oh, right. Okay. So I think I have. I will do this right here. Now this is actually going to print. It's going to run through this process where it's still a pass-through eval, but we're going to implement the read and the print. So given a tree structure representing the expression that we parsed, we're going to print it. And so you can see it's gotten a little bit more complex, although the shell of our interpreter has not changed at all. Well, it's not changed much. So here's step one, which is just read and print. The only difference is we're delegating to this printer object that we imported, and we're delegating to this reader object. So if we look at our reader, the core of the reader just either reads an atom or it reads a list. And that's it. If it's an atom, it just reads it as the atom. If it's a list, it reads it as a list of other things. And so it's just a very simple tree branching structure. And one of the nice things is this is the regular expression that is appropriate for MAL syntax and will recognize each individual atom. And so the core is this function read form, and we just say, if the current token is a left paren, read it as a list. Otherwise, read it as an atom. And read list just walks through each item in the list, calling read form on it. So if it's not, while it's not this, we actually just call read form and we append to the list, and that's how you read a list. So I mean, this is really, you're just building a tree structure. It's actually simpler than a JSON parser, much simpler. And then the print is even simpler, where if it's a list, we're just going to wrap parentheses around it, and otherwise we're just going to print the string associated with the atom. So the result of that is that if we now run our REPL, an atom is just an atom still. But if we say foo, it parses it as a list, but you can see that if we add spaces there, it's still recognizing that this is a tree structure, and it's taking out the white space. And so the white space is what's separating the atoms from each other. And I believe if you have, it now will throw a syntax error because it's saying, hey, I was expecting to read a list, and I never got that list. Ironically, it doesn't care about, it just ignores trailing parentheses. But you can see now it takes you to the step where you've got abstract syntax tree. That's really, I don't know, it's nice because it's a baby step, but it's actually a pretty nice step. So now we're dealing in trees. And then the next step, step 2, which is I think where I am, is where you're actually doing, so the cool thing about here is we're actually recognizing, is this a list? Is this a symbol? Is this an int? So you can't see this, but internally it knows that that's an integer. It knows that, what's that?
Are those kind of like the primitives in Lisp? Like what if any primitives are there?
In Lisp, there are lists and atoms.
That's it?
And then, no, there are, so you can have an atom be and it can be a symbol, or it can be an int. Or it can be a number. There's a couple primitives. There's a vector, and now there's a hash map. So you can actually have hash maps. I haven't gotten to that yet. But vectors evaluate to themselves. But we'll get into that when we talk about evaluation. And that's the other thing. So when you get into step 2, sorry, you're actually going to do a evaluate step. So in step 0, we set up the read eval print loop. In step 1, we made the reader actually take the string and parse it into an abstract syntax tree. And we made the print take an abstract syntax tree and print it into a string. And so now we're actually going to have a evaluation step in the middle where we want to take that tree and reduce it into a value. And so what you're going to do is you have what's called an environment, and that's where symbols live. And so the reason that's important is the evaluation rules. And the evaluation rules are really simple. If you have an atom, or sorry, if you have a literal, like an int, or a number, or a hash map, or a vector, it evaluates to itself. If you have a symbol, it looks up in the environment, and it evaluates to whatever is in the environment off of that. If you have a list, it evaluates all of the items of the list, and then calls, and then the first member of the list, it calls as a function with the second, with all of the arguments all of the remaining members of the list as arguments. So there's only really 3 evaluation rules in Lisp. If it's a literal, it evaluates to itself. If it's a symbol, it looks it up. And if it's a list, it evaluates all of the members of that list. It calls eval on all of the members of that list, and then assumes that the first one is a function, and then calls it. So what they have you do is create the math functions up here. So if I go ahead and create this in step 2, you can see I have this REPL environment. And so I've got these strings plus, minus, star, and divide. And so what happens is inside of eval, so read and print stay the same, but eval is a little bit different. If it's a list, if it's not a list, I want to evaluate it. I call this eval AST. Otherwise, if it's a list, if it's empty, I return the empty list. Otherwise, I evaluate, I call eval AST on the list, which evaluates each member. And then I take the first member. This is a little bit of Lisp. I used cons, which is the first member of a list, and cdr, which is the last, the remaining values, but then I apply them. So what you can see here is what that means in real terms is that if I look up the symbol plus, it's going to return this function. If I return the symbol minus, it's going to return this function. And so if I have foo, whoops, let me restart my REPL at step 2. If I say foo, now it's like no such value for symbol foo. It's like trying to evaluate that. It actually like looked it up in that environment, and all there are math symbols. If I have plus, it looked it up. I actually don't have a type for a mal function yet. This is actually just a JavaScript function. But you can see if I say plus 1 1, it's now going to return 2. And if I say like plus 1, it's saying, hey, that's not a function. If I say 1 2 3, one's not a function, so I can't call it on two, but I can do like, do division. And it supports, so I can say 3 times 2, and then, that's going to be 6 divided by 2, should be 3. Yeah. And so it's actually it's like a shockingly small amount of code that has to go into that evaluation there. And that's where I am right now. And I think I'm curious what happens if I say, foo12, no such value. So it's actually trying to look up the value at foo. It never got to the point where it tries to call foo as a function. But I think that's neat in the sense that you get to see kind of how these simple evaluation rules get to like feed into how function calls happen, and how every single Lisp program is basically this one syntax tree, and you're just calling eval on it and you're reducing it. And that's, when people talk about the lambda calculus, that's what it is you've got, you have some expression and you're giving it some variables, and then you just kind of like keep recursively evaluating it until it can't be reduced any further. And that's what it's all about. And Lisp has stuff like macros and reader macros and what have you layered on, but this is about as close to the metal, as the computational metal, as you can get. And the cool part about it is it's not like it's more complex, it's actually less complex. And you get to do it yourself. And the thing I like about this Make-a-Lisp program is it gives you very concrete steps to achieve and to follow, and it gives you a test suite so that you know if you're on track at each way. And it's got implementations in other languages if you need to crib off of those. And so I just think if you're going to climb the Lisp mountain, it starts you out at base camp and gives you a roadmap all the way there. But you still get to have every bit of insight along the way. So that's pretty much it. Are there any questions or?
It's pretty cool.
That's pretty awesome.
Yeah, I really recommend it. I was surprised at how easy it was to get set up and going. Well, there was a little bit of pain getting the test harness set up, but.
Do you recommend this to somebody who's never done anything with functional programming? Like, I've never written a line of Lisp. I've never read SICP or whatever. Like,
I think it's actually a better place to start.
Okay.
Yeah. Because yeah, I think it might even be a better place to start. Was there, because one of the things that blew me away is how simple these things are, and people get wrapped up in all the stuff that's built on top of this. But this kind of reminds you, okay, it's very simple. It's very simple, these ideas. We read, we print, we evaluate, we look up in it from an environment. Like,
pretty zen.
Yeah, it's very zen. So I'm looking forward, and I would say the sum total of the amount of work here is, I don't know, maybe 3 hours, 3 or 4 hours, like grabbed to this point. Yeah, I would say it's two, maybe a little bit more, maybe like two 2-hour sessions in an evening, and then an hour here and there. But it's definitely less. It took definitely less than 7 hours to get to this point. And the best part is it actually feels like you accelerate. Like once you actually get the read, evaluate, print, the reader and the print, I would say the reader was the hardest thing to implement. And then the evaluation took 30 minutes to do. That was actually surprising, is like as you climb, it's not harder, it's easier. Because you're building on stuff. So I'm curious. I actually haven't looked that much further on what the different. So step 3 is environments. So I guess it's making the environment a little bit more complicated. Step 4 is function application, tail call optimization. Yeah, you get it. Files, mutation, and evil. And the other thing I like about it too, that's actually a great point, is you don't have to make any decisions about like the syntax. Like there are many dialects of Lisp, and like this is one of them, and you don't have to make any decisions about, oh, do I want this to behave differently than other Lisps? It's like, no, these are the set of semantics like you're going to implement, and you just do them. So you just do them. Whoa. I'm trying to see if there's any live chat, or is that where it is? Ah, there it is. Okay. Whoa. What's that?
Yeah, somebody's watching this on their phone.
Huh. Interesting. Shout out to the person walking and watching the Lunch and Learn. So yeah, are there any questions? Oh, hello. Nice. So yeah, I would recommend this really to anybody who wants to give it a shot. We can't. No, they're muted. Okay. Alrighty. Well, I will go ahead and stop the screen share. And yeah, if I really like it's a great little thing that you can do in your side time, and it will guarantee.
You guys trying to talk.
Yeah, are you trying to? Oh, you know what? We can't hear you because you're on mute. I can't unmute him, but for some reason you're muted. There you go.
Oh yeah, it must be.
Is that you, Alric? Not sounding good. Yeah. Okay. I'm gonna. Well, the problem is with the broadcast. Let's see. Yeah, seriously, AT&T has let us down today. Yeah, boy, I can't hear anybody. Yeah. Where's the chat? Well, the problem is we have someone on mobile. You can't really talk or can't really chat. Yeah. Okay. Sorry, Elric. Yeah. All right. All right. Bye, everybody. Thank you. Where did I?